So our next team is the Seas Grace team, and they are working on climate research, weighing where the water goes with the Center for Space Research.
Hi, my name's Lindsay Beer. I'm from Vermont.
My name is Anjali Koda and I'm from Dallas.
I'm Ayush Deshmukh and I'm from Austin.
My name is Vardhani Karthik. I'm from California.
And together we are the Grace team.
So last summer we participated in the NASA STEM Enhancement in Earth and Space Science High School internship. And again, we are the Grace team. So our goal last summer, or our goal in general, was to work towards answering the ultimate question of whether machine learning methods can be used to identify changes in groundwater storage shown in the GRACE satellite data. So that's a pretty lofty goal. So last summer, we were just taking the preliminary steps towards answering that question.
Yeah, so like Anjali said, we're only taking the first steps towards that goal. So our question last summer was, can a machine learning algorithm be used to learn anything about hydrological signals seen in GRACE data? And to explain our answer, we're first going to walk you through what the GRACE mission is. Then we're going to talk about the GRACE satellite data as well as another model data set called Aohis. Then we're going to compare the data in different locations. And then we're going to explain our test that we used to answer the question, which was, can a neural network sort the data by month?
So as Vardhani said, we're going to start by talking about the GRACE mission a little bit. So GRACE stands for Gravity, Recovery, and Climate Experiment, and it consists of two missions. The first was GRACE, which was launched in 2002 and ran until 2017. And then GRACE Follow-On was launched in 2018 and is still running today. As you can see in the diagram to the right here, each mission consists of a set of twin satellites, and the distance between the satellites is calculated, which can detect groundwater storage, water in lakes and rivers, moisture of soil, changes in sea level, and ice melt. What's important to recognize is although the change between these satellites looks pretty dramatic, the satellites can actually detect changes that are as small as 1/10 of a human hair. Another important note is that official global solution is released every 30 days.
All right, so now that we kind of know how the GRACE satellite works, let's kind of explain how it actually detects changes in gravitational field. So basically the satellites constantly measure distance between the two of them as they orbit the Earth. And as you can see in the graphic, the red arrows on the satellite indicate horizontal speed and the blue arrows indicate the gravitational pull on satellites by mass distribution on Earth. So in panel one, both satellites are the same speed, they're moving in phase, so there's no noticeable difference in the distance between them. But as they approach the second panel, as the first satellite approaches the landmass, the gravitational pull causes it to accelerate, increasing the distance between the two satellites. Then in panel three, once the first satellite has passed the landmass and the second satellite is approaching it, the distance is squeezed together again because the first satellite is pulled back, the second satellite is pulled forward, and you can see this close of distance in panel four. So gravity causes all of these changes in distance. So measuring the distance between the two satellites allows us to see how gravity fields on Earth change over time.
So those satellites are mostly affected by changes in water storage and not so much by land masses, except for a few cases such as earthquakes. And when that happens, we have to isolate that variable from the measurement. So basically, we measure these changes in water storage as equivalent water thickness, which are mass variations from a baseline in terms of a measurement of the height of a thin layer of water at the Earth's surface. And we measure all of that in centimeters. So if we look at the right side of this slide, the first thing we can see are these plots for January, February, and March of 2012. And if we look at the scale, it ranges from -20 to 20 centimeters. Positive values correlate to an increase in equivalent water thickness, and negative values correlate to a decrease in equivalent water thickness. So if we look at the plots themselves, most of the world shows a low amplitude signal, except for a few places. So if we look at the Amazon, it shows a high increase in equivalent water thickness for that month. And then Greenland, for example, shows a decrease in equivalent water thickness for that month. So that being said, GRACE is a first of a kind mission, and it still has some limitations.
So one limitation of GRACE is we don't know if we have enough GRACE data to complete machine learning tasks. And this is because GRACE started in 2002, and the data collected from 2002 isn't enough to capture all the possible hydrological events that can happen on Earth. So the solution to this problem is model data, which can span further back in time. And eventually, we want to augment the model data with the GRACE data to use as training data for machine learning tasks. And for right now, we're going to be starting off with the Aohis model data set, and we're going to use this because it is very similar to GRACE. And we're going to be explaining more about this in the next slide.
So a little bit of background information on the Aohis dataset. It's a model dataset for water mass variability, and it was created by the European Space Agency, and it began in 1995. So Aohis stands for A, atmosphere, O, ocean, H, terrestrial water storage, which includes groundwater, snow, surface soil, moisture, things like that, I, continental ice sheets, and then S, solid earth. So Aohis this model data set produces data every 6 hours, which is its temporal resolution, and its spatial resolution is 50 to 250 kilometers.
So we compared the two data sets to answer the question of can we learn about the GRACE data set from the Aohis data set, keeping in mind that eventually we want to augment GRACE data with model data. And we found that the main differences were that Aohis is a synthetic model data set, and it ran from 1995 to 2006, so an earlier time frame. And then GRACE is from 2 real-life satellites and consisted of 2 missions, the first from 2002 to 2017, and the second from 2018 and is still running now. But what's similar about both of these data sets is that they both quantify mass changes around the world.
All right, so now that we know what GRACE and Aohis are, we wanted to see the data they collected, right? Especially we wanted to examine whether our future neural network performs better in some regions than others. So we plotted and compared the measurements for equivalent water thickness for 4 different regions around the globe, including South America, the Middle East, Australia, Greenland, and we also zoomed in on a smaller section of South America that predominantly included the Amazon rainforest. Okay, so here are the plots and graphs for our results for equivalent water thickness. As you can see on the y-axis, the data points for equivalent water thickness represent a change from a running average for each month or a mean field, so they're not absolute values. And then in the data trace, you can see that red is Aohis and blue is GRACE. When we analyze the graphs, we can see that seasonal variations in each of the graphs, so like a sinusoidal pattern, demonstrate that there's like a signal to be learned and analyzed by our eventual neural network. The peaks and valleys in equivalent water thickness change and occur at the same times. And when we compare GRACE and Aohis directly, it's pretty clear that Aohis models GRACE very effectively. Beyond just comparing GRACE and Aohis overall, there are some interesting features on each of the plots that exemplify how fluctuations in equivalent water thickness might cause our future neural network to analyze some regions better than others. As you can see in Australia's plot, there's a large spike in equivalent water thickness around 2011, which we were actually able to trace back to the Queensland floods in the Lake Eyre Basin. Additionally, Greenland's graph shows a drastic downward trend, causing Aohis data to fail in overlapping GRACE data at all. This could possibly be due to ice melt, which has affected Greenland much more severely than the other regions we studied. These findings represent the perfect segue into the machine learning phase of the project, as we now fully understand the behavior of equivalent water thickness values for each of these regions, and now wanted to explore whether we could glean any insight about these regions using neural networks. Before we move on to the neural network slide, we did look at that smaller section of South America that included the Amazon. And what we found was that the range of equivalent water thickness values was much greater for the Amazon section, which is kind of expected when you examine a rainforest in isolation. But as you'll see later on our neural network plots, this did not really have any effect on our training or testing accuracies.
So in the last couple slides, Aohis talked about some events such as droughts and floods that caused big changes in equivalent water thickness. So by looking at this type of data, scientists are able to identify these events, but only way after they've happened. So it would be really helpful to predict them or recognize them in real time. Again, that's a pretty lofty goal. So this summer, we were just trying to see if we can learn anything about GRACE data from model data and whether a machine learning algorithm can sort satellite data by month. So the answers to those questions will help us eventually find out whether we can augment satellite data with model data and to identify those events in real time. So this is where we began the machine learning part of our project, which is basically the development of a program with the ability to automatically learn and improve from experience without being explicitly programmed. More specifically, this is where we started working with convolutional neural networks, which Lindsay will explain in a later slide.
So before we talk about the neural network that we created, I'm going to explain how a neural network works. So in a neural network, there are 3 stages: training, testing, and actual use. So for training, a neural network uses data that has a given output or given input and output, and it optimizes its weights so that the input matches the desired output as closely as possible. For testing, the neural network takes a portion of the training data that hasn't been used yet, and it has fixed parameters from the training stage, and it evaluates the accuracy of the network. For actual use, the neural network classifies as new data that doesn't have a given output, and it does this with an already trained and tested network. So before I said that testing used data that was a subset of the training data, but for our experiment, we're going to be using the Aohis data for training and the GRACE data for testing, which are different data sets. And this is because we want to see what we can learn about GRACE data, which is satellite data, from the Aohis data, which is model data. And we want to do this because if we can learn about GRACE data from Aohis, then we'll be able to use both data sets together as training data for future machine learning algorithms.
So as Anjali said before, we used convolutional neural networks primarily in the machine learning part of our project. And as inputs, we used images of grid maps, such as the one on the left side of the screen here. This is actually an example of South America. We did remove the border lines because we don't need the computer to recognize them. What's important to note is as the inputs, we use pixel values instead of equivalent water thickness, which is measured in centimeters. The goal of the neural network was to match images of grid maps to the month that the image was taken. And looking at it from a more general view, convolutional neural networks are composed of convolutional layers, which help pick up on features of the image. Then through a process called pooling, these features are resized as the convolutional neural network runs. Eventually, this leads to the outputs, which are the matching the images of the grid maps to the month that they were taken. The highest probability is considered the accurate output by the neural network. We started off by training our neural network, meaning that we took Aohis images in each region that we had pre-sorted by month and incorporating them into our code. We then tested our neural network by using GRACE data images to see how well our neural network was able to differentiate images by month. We're now going to explain what we found for each of our regions.
All right, so now that we kind of know how we went about the process of analyzing these regions with our neural network, let's graphically take a look at the results of our neural network, testing and training for the 5 different regions of equivalent water thickness that we examined. If you take a look at the graphs, the y-axis shows a percentage to represent the accuracy of the neural network in identifying the monthly images. The purple line that you see on the graphs represents the training values for accuracy, and the blue line represents the testing values. Meanwhile, on the x-axis, you can see the results of the neural network for each epoch, which is one cycle of training and testing. When you evaluate the graphs as a whole, you may see that our maximum testing accuracies are topping out for each region at about 35%, which isn't really perfect, but it's still encouraging as it shows that our neural network is learning something. Otherwise, our accuracy would stand at the random guessing rate of about 8%. Additionally, we trained our neural network on 144 total Aohis images, whereas most neural networks train on tens of thousands of data points. This could be a potential culprit for the overfitting you see in the graphs, where the training accuracy far exceeds the testing accuracy as the epochs progress, simply because the network memorizes the training data set instead of actually learning from it. Additionally, you can see that Greenland has pretty extreme overfitting, which can be attributed to the ice melt we talked about earlier and the bizarre graph that we had for the plots. Overall, these graphs show a positive result for our machine learning analysis.
From all of our experiments, the machine learning graphs and the equivalent water thickness plots, we can conclude that Aohis can model GRACE reasonably well. The average accuracy for training was about 87% and testing about 39%. Although these accuracies weren't perfect, they were definitely better than randomly assigning an input to a month, which would be about 1 in 12 or 8%, as Ayush said. Because out of 12 months, there are 12 possible outputs. We did have overfitting, but that was largely inevitable considering our small sample size and that our training and testing data sets are different. In running future experiments, there are some improvements that we could make that could maximize accuracy. And these include trying other model data sets, specifically ones that go further back than 1995. We could also apply changes to the neural network, such as architecture adjustments, adding additional layers or filters. We could also try removing the linear trend on Greenland, which would allow us to solely look at the seasonality. Lastly, we could use equivalent water thickness data points instead of the RGB pixel values that we're currently using.
So that wraps up the machine learning part of our project. And lastly, we just wanted to go over some reflections we had of the program. I personally really enjoyed doing work that had real world applications and also working with real satellite data because I've never had the chance to do that before.
I personally enjoyed working with team members, like working together with team members instead of just dividing and conquering of a project.
I really enjoyed working with machine learning as it's really a cutting edge part of technology, and I believe it's part of the future.
And then coming from a rural state like Vermont, opportunities are limited and there's certainly no program like this. So the chance to work with other highly motivated students on some pretty amazing work is a once in a lifetime experience.
All right, before we go, we'd like to thank Corinne, Julian, Miss Baggio, and Miss Miller and the entire SEAS program. And we want to thank you for listening to our presentation. Does anyone have any questions?
So one of the questions would be, how have you taken what you learned in SEAS and applied it to other things that you're learning about in school this year?
I guess I can start with that one. I participate in a robotics competition at my school, and I've actually used the machine learning knowledge from SEAS to incorporate into our code for our robot, especially in the autonomous period of our game.
I can just add on to what Lindsay said. Beyond necessarily technical skills, I think presentation skills were a big thing that we all learned over the summer and leading up to this presentation as well. And that's been really helpful in any presentation I've given at school. I feel like I'm really prepared for it.
So we have another question. What was the biggest challenge that you faced while conducting your research?
I guess I can start again here, and then Vardini, you can hop in. I think there were two things that stood out to me the most. One was we got very different results on the different computers that we would use. And so trying to find a way to make adjustments to our code to get the same results. And then also in the beginning, starting virtual, it was really tough getting to know each other and work together. So we played Cards Against Humanities, and that certainly helped, but overcoming the team challenges was definitely an important thing that we came out of the summer with.
I'd say also just the idea of coding itself. Personally for me, I didn't know how to code before this program. I think that many of us had limited experience with coding, and then being able to learn coding as well as being able to create a machine learning algorithm for satellite data was pretty impressive to all of us, but it was a challenge in getting there.
And so the last question would be for each of you. What are your career plans?
I can start. I feel like that's like a pretty big question, and like kind of like top down looking. But for me, I really just enjoy problem solving in general. So I think like engineering or going into consulting or something like that exemplifies the ethos of just solving problems. And so that's something I'd really be interested in.
Yeah, I think I'm gonna have to agree with Ayush. I mean, I've always had an interest in the environment and also in I like coding, so something along that route. But this program was really helpful for me to discover that.
I have always had an interest in biomedical engineering, but I never really saw how I could incorporate coding into it. But after this program, I'm definitely more interested in like an AI or something in that route.
Personally for me, in the beginning, I had like a dislike for coding, I guess. And I knew I wanted to do engineering. But then after this program, I realized that I actually did like coding and I want to incorporate that in the future.
Well, congratulations to each of you. You've done an excellent job with your research, and I think that everyone would agree we've learned so much by your presentation today.